Good. So we're starting chapter 5. We're talking about relationships within a triangle. Okay. Today we're going to focus on perpendicular and angle bisectors. Actually, today tomorrow we'll focus on those. And you should already know what a perpendicular bisector is. You should know what the word perpendicular means. You should know what the word bisector means. Maybe not. I don't know. So hopefully, if you don't know, you will learn. But a perpendicular bisector is a line, a segment, or a ray that intersects a segment at its midpoint and is perpendicular to the segment. Okay? Now, this first picture here, it states that PQ is a bisector of AB. So that means that PQ is bisecting AB. It's going through AB's midpoint, which looks like it's P. Okay? And when you bisect the segment, you go through its midpoint and you break it into two congruent segments. Now, they're not both bisected, only the one that's being bisected, which would be AB. Okay? Alright, so this is just a bisector. Now, if you look at this one, it says RS is a perpendicular bisector. Okay? And a perpendicular bisector also goes through the midpoint, creating two equal parts of what's being bisected, and it creates four right angles. Okay? Everybody remember, this is the symbol for perpendicular. Okay? Make sure everybody knows what that symbol is. So, this is a perpendicular bisector. So, RS is going through JK at its midpoint, which is R. So, it breaks it into two equal parts, and it creates four right angles. So, that's what a perpendicular bisector does. Okay? Alright. Then we have the perpendicular bisector theorem. Okay? And it says, if a point is on the perpendicular bisector of a segment, then it is equally distant from the endpoints of the segment. Okay? So we see PQ, right? PQ, and it's intersecting XY at its midpoint. Because these two segments are congruent. Okay? XQ and YQ are congruent. It's also perpendicular to it. So this right here is the perpendicular bisector. Okay? That line L or line PQ is the perpendicular bisector. Okay? Alright. Now, this theorem says that any point that lies on that perpendicular bisector is equidistant from the endpoints of the segment that is bisected. So this point P is equidistant to X and Y. So those two segments are equal to each other. I could draw another one right here. Okay, we'll call that one T. Okay? This point is also going to be equidistant from the endpoint. Alright, so any point that lies on the perpendicular bisector is equidistant to the midpoint. Alright, the converse of that states that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. Okay, so this is looking at it backwards. Okay, we see here that this point P is equidistant from X and Y. Okay, and that tells me that the line that this lies on that intersects this segment is the perpendicular bisector. So that means that when you draw it, so if it intersects XY, it's perpendicular and it bisects. Okay. Alright, so let's look at a couple of questions here. Find each measure. We want the length of AB. Well, notice that AC intersects BD at C. Okay? And it's perpendicular and also breaks into two equal parts. So what does that say about point A? That it's equidistant to both sides. So if this side is 4.1 and this side is 4.1. Okay? Alright. WY. Okay, we come over here and we see that X is equidistant to the endpoints of W and C. So what does that mean that this segment does, this line does? It bisects WY and YZ, and it's also perpendicular to it, right? So what would the length of WY be? 3. What would the measure of angle XYZ be? It's perpendicular to it, which means it creates a right angle. Okay, here's another one. RT, we want the length of RT. Now, notice that RS is perpendicular to QT and it bisects QT because these two are congruent. So what does that mean about QR and TR? That means that they're going to be equal to each other. So if I want to find the length of RT, I need to find X, right? So what am I going to do to get X? Set them equal to each other. So I get 2X plus 3 equals 4X minus 7. And so subtract 2x from both sides, add 7 to both sides. So that gives me 10 equals 2x. Divide both sides by 2, and x is 5. Okay, is that my answer? No, I need RT, so that means I got to go back and plug in. And I have to do 4 times 5 minus 7. So that's 20 minus 7, which is 13. Okay, now this one requires a little bit more thought. We want the length of OL. Okay, so this right here is what I'm looking for. Okay, so let's start with the big picture. If we look at this big picture, what kind of triangle is this? Okay, it's an isosceles triangle, right? Which means that K is equidistant from J and L, right? Which means K lies on the what? The perpendicular bisector. So if JN is 14, what's in L? It's 14. Okay? Now, let's look at this triangle. Okay? It's also an isosceles triangle, right? So that means that this right here is the what? QN is what? It bisects. It's the perpendicular bisector. So that means each one of these parts is going to be what? A step. So OL is going to be 7. Alright. Mr. Lee wants to park his ice cream cart on Main Street so that he is equidistant from the entrances of the amusement park and the zoo. Where should Mr. Lee park? How can he determine where to park? Okay, so here is the zoo entrance and here is the park entrance. Okay? And Mr. Lee wants to park his truck so that it is equidistant to the two entrances. Okay? So here is the segment that connects the two entrances, right? Where we have any idea where we should put it? Yes. Okay, but he wants to be along Main Street. Move it up from there, how? Okay, because here's the midpoint right here. Okay, we'll say this is the midpoint. Okay, that bisects it. What else do I need to do? It's got to be a perpendicular bisector, right? So it's got to be a perpendicular bisector. So then no matter where I put this truck, it's going to be equidistant to the entrances, right? So he wants to get along Main Street, so we can put him right there, right? We're going to put Mr. Lee right there, okay? All right, so figure out how far apart the entrances are, find the middle, and then make a perpendicular bisector. Put this truck anywhere along there, and it's going to be equidistant to the two entrances. Okay, so here's another question. The entrances are 40 feet apart. Mr. Lee decides to move his cart off Main Street. How can you find where Mr. Lee should park if he must be 30 feet from both entrances? Okay, so we're going to move him up. He wants to get off of Main Street. And we want to put him in a place that's going to be 30 feet from both entrances. Okay, and it says that the distance between the parks is 40, right? So if this is the midpoint, these are both 20, yes? Okay, so how should we figure out where to put him so that he's 30 feet from the entrances? We're going to have to figure out. How long? Keep going. Instead of being down here, we're going to move him up, but we don't know where to move him, but we want this distance. Okay, but how are we going to do that? triangle are we working with right here? Right here. It's a right triangle, right? And we know that this leg right here is 20, and we know that the hypotenuse is 30. I need to figure out how far down the perpendicular bisector he needs to go to be 30 feet. What am I going to do? It's a right triangle. That should be a really big clue. Oh, not necessarily 45, because it's not really limited to the isosceles. Stop under the hypotenuse. Well, but I don't know how far to go down. I don't even know how far that was, right? But I know that I want to be in a spot that's 30 feet away from both entrances. Yes. Yay! The Pythagorean theorem. Okay. If you have a right triangle and you know two sides of it, you do the Pythagorean theorem to find the third side. Yes. Okay. Because this is what we have going on right here. This is 20. This is 30. We need to know what that is. Okay. So we're going to do leg squared plus leg squared equals hypotenuse. So that's x squared plus 400 equals 900. Subtract 400 from both sides, and that's 500. And then take the square root. The square root of 500. What? 25? 25 times 25 is 625. 22.4. So, 22.4 feet. So we need to go to the midpoint between the two entrances and go down 22.4 feet. And that would be approximately 30 feet for both entrances. Would that ever be useful in anything? In construction and like maybe working with gas lines and all that kind of stuff, aren't there requirements on like distances things have to be away from each other?
Navigation.
Yeah. Huh? Sure, navigation. Yeah. So lots of different ways that can be used. Okay. Now we want to talk about angle bisectors. We talked about these before. Okay. An angle bisector is a line, a segment, or a ray that divides an angle into two congruent angles. So we have a big angle, right? We have a big angle, and BD is in a bisector. That means BD goes where? Where is it? You're talking like, not math language, but if I bisect an angle, I'm going to draw this so it goes where? Right through the middle. We don't have a term for that, right? It just goes right through the middle. It's bisecting it, but it goes right through the middle. So it takes that big angle and makes what? Two smaller ones that are the same, right? It is half, but I want you to get to where you bisect an angle, it creates two congruent angles. Yes, one, the smaller one is half the larger one. You need to know that too. But when I bisect an angle, it creates two smaller angles that are congruent to each other. Okay, that's what bisecting is. And we have the angle bisector theorem. It says if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So again, we have this triangle ABC, and BD is bisected by the symbols, right? Any point that lies on this angle bisector is equidistant to the sides of the angle. The sides of the angle are the rays that make it up. So this distance and this distance, and it has to be the perpendicular distance, because that's the true distance, has to be the same. Okay? So if you bisect an angle, any point on that bisector is to the side. So I can pick another point. Let's call this E. If this is an angle bisector, then this distance and this distance is going to be the same. Okay? That's the angle bisector theorem. I think it's theorem 5.3. I forgot to put the new theorem number on there. But we'll just call it the angle bisector theorem. The converse of this is also true. If this is 5.4, okay? If a point is in the interior of an angle, that means it's inside the rays, and it's equidistant from the sides. Equidistant means equal distance. Then it is on the bisector of the angle. So we have this point that is inside the angle. when we see that this point is equidistant, the same distance from the two sides, then I can draw a ray or a line from the vertex through that point, and it is going to be the angle bisector. Okay? So if you have a point inside the angle that's the same distance from both sides, then I can connect the vertex in that point, and that will bisect the angle. Okay, find each measure. Angle ABD is what we're wanting. Okay? Now notice, BD is a ray that's been drawn. This point D is equidistant to ray BA and ray BC. So what does that tell me that BD does? It bisects the angle, which means angle ABD is what? You approach the other one, it's going to be 37. Okay? So 37 degrees. Okay, look at this next one. Again, we have triangle ABC. We can see that BD is a bisector. See how these two angles are congruent? That means that BD is a bisector. And that means that D has what relationship with A and C? They're congruent. This is a perpendicular distance, this is a perpendicular distance. Because this is an angle bisector, these two distances are the same. So, I want to find the length of CD, which means I have to find X first. What am I going to do to find X? Set AD and CD equal to each other. So 3X plus 5 equals 6X minus 7. So that ends up being 3X equals 12. Divide both sides by 3, and X is 4. Is that my answer? No, I'm still looking for CD, so I got to go plug it in. Okay, and that would be 6 times 4 minus 7. 6 times 4 is 24. Minus 7 is 17. So CD is 17. Okay. Okay. An airport baggage inspector needs to stand equidistant from two conveyor belts. How can the inspector determine where he should stand? Okay, so here's a conveyor belt in the airport. This is the inspector. He wants to be the same distance at all times from both of the belts. Okay, so we want this distance here to be the same as this distance here. We want that to be the same. Okay, so how can he determine where to stand? Okay, if we were to draw the angle bisector, then he can stand anywhere along there, and at any point he would be equidistant to the two sides of the belt. So let's say he wanted to stand here. Okay, well he still is going to be equidistant to the two belts. Okay, anywhere along that line, he's going to be equidistant to the two belts. Okay, consider two triangles that result from drawing perpendicular segments from where the inspector stands to the conveyor belts. That's what I drew in the blue here. Okay? How are these triangles related? So we have, we'll call this the red triangle. Okay? And we'll call this the blue one. Okay? They are both right triangles. Okay? We know that they have a right angle. We know that these two lengths are the same. Okay? They share this length right here, so yes, you could use hypotenuse leg. Could I use anything else? What did I do to create that line, that other red line? What did I do to create it? I bisected the angle, didn't I? Yeah. So what do we know about these two, blue and red? They're equal also, right? So I could have used what? AAS or hypotenuse leg. Okay? So I could have used an AAS or hypotenuse leg. All right. Any questions? Okay, I do have one more question to ask you. Somewhere. How do you area of a triangle? Base times height divided by 2. What has to be true about the base and the height?
They have to be
they have to be perpendicular. Okay? So the base and height have to be perpendicular to each other, so base has to have height.